Let me say good morning to all of you folks, and despite the short night, I'm very glad to welcome you here. This session is quite atypical. Well, perhaps in a few years from now, all the session will be like that. We have a video conference with Anna Preston. She is from the University of Tennessee, where she is research consultant, and she is much involved in Internet 2 activities, where she is program manager for international affairs. She will be speaking about peer-to-peer technology. 30 minutes, Anna, 5 minutes question. And if I raise my hand like that, it's 10 minutes. Like that, it's 5 minutes, okay? So, Anna, please, carry on.
Thank you very much, Jean-Paul. Good morning, everybody. It is indeed very early here in the United States. Thank you very much for the opportunity to talk to you. I wish I was there in person. I'm wearing my green for Ireland here, and in any case, like Jean-Paul said, I'm currently on loan to the Internet 2 project in the U.S. I am program manager. What I will talk about will be based also a lot on work that I've been doing at my university, and so let's go ahead and start. Just a second. Okay. First I should clarify that whenever you see that P2P, or I refer to P2P, I am meaning peer-to-peer. Basically, what this talk is going to be talk about is about this thing that people have assumed must be disruptive. And what do I mean by that? Well, there's been a lot of interest and hype around how profile file sharing applications, I'm sure everybody by now has heard of Napster, and the potential that they have for disruption. People have called peer-to-peer unsecure, unscalable, and unmanageable. I like to think that there is a host of positive new opportunities in many areas. I think it's interesting that people, to some extent, are also calling peer-to-peer what could be possibly the third generation of the Internet. The first generation being the raw Internet for only a few selected users, computer users. Perhaps the second generation being best labeled as the web and the explosion of the Internet, and the third generation really being things about making new services to users that are available in a cheap and quick manner, and by making the use of the PCs of these users as active participants in computing processes, rather than just passive web browsers. And in some regards, peer-to-peer is doing this in radical ways that shake up the traditional way of doing businesses. For today's talk, here's an outline of what I would like to talk about. Like many disruptive technologies, I think peer-to-peer suffers from a lot of ambiguities in defining the core technology and where it is today. I think in this talk, I would like to take a stab at giving an overview of peer-to-peer computing and comparing different peer-to-peer networks and applications. I also would like to look at some of the technical hurdles that peer-to-peer must surmount. What I mean by that is upsides and downsides to some models, and perhaps just, if time allows, cover some of the more social challenges while also covering the opportunities that could be for the advanced networking community. A few words on peer-to-peer. Peer-to-peer is not necessarily a new concept or a new phenomena per se. One may argue that it's been intertwined with the development of the Internet from its inception. I may be stretching this a little bit too far, but for purposes of this talk, allow me to stretch this. For example, in 1969, we have the first peer connection attempted through the ARPANET between independent computing sites. This occurred between UCLA and the Stanford Research Institution, with the first attempt being the logging, as one might suspect, which incidentally caused a system crash. Further in the 70s and 80s, we see the development of Usenet and DNS. I think what is relevant with regards to peer here is that to some extent Usenet and DNS exemplify some of the aspects that we see in peer-to-peer applications today, those being decentralization and limited central control to some. But the sudden commercialization of the internet in the mid-90s sort of imposed client-server super infrastructure. Towards the mid-90s, we see the development of ICQ and how something like ICQ bypasses DNS and somehow starts allowing for endpoints to be directly addressable with each other. And then, of course, we see other things like Napster, which really moved towards a more end-to-end, sort of decentralized communication, taking advantage of endpoint resources. Well, you guys read this cartoon. I think by now everybody knows the history of Napster. I hope you can read this very well. If not, it'll be available later at the website. But Napster is born in 1999, and today is 2002, and it seems that Napster is gone. What's interesting is that in between 1999 and 2002, one can see a whole bunch of things happening. It's interesting to notice how universities were the first to notice Napster and things like Napster, and today universities are sort of the ones living firsthand sort of the repercussions, some of the things that came out of Napster, and of course other variety of applications have emerged since the year 2000. What's interesting too, I was doing some research on this, and this is a quote from, well, not too long ago, but quoting a survey from WebSense indicating that the number of file swapping and peer-to-peer websites had grown by more than 535% in the past year, despite all the legal efforts to have these things shut down. I think it's an interesting statement. This slide was supposed to show the simplest form of peer-to-peer is really two computers talking to one another. I was very proud of my graphic there, but it didn't show up. Really what I want to talk about here are the different models or frameworks within peer-to-peer architectures. There's really three, in my opinion: the centralized, the decentralized, purely decentralized, and then something in the middle, a hybrid type of models. For the purposes of the next slides, there are some components that are shared within all of these. Some of them may just have client and server, like the centralized model, and servants, a client that can also act as a server. The main differences in how this categorization is taking place is on, or how I'm framing these frameworks, I suppose, would be on how the information is shared and how much information is shared. In a centralized system, and for now as a clear example, we have something like Napster, users use centralized servers to keep a catalog of available files. Really, the way this system works is a user will submit a request to search for a particular file. The central server will create a list of files matching that request and will bounce back to that user by looking at its database the list of files that belong to users who are currently connected to the network. So let's see. Then we have that the requesting user can then select the list or that file from a list of people or users that have that file, and then that requesting user can then open a direct connection with the individual computer which currently possesses that file. The download of the actual file takes place directly from one network user to the other one. In this model, without a central server, the network does not necessarily function per se. The size of this model can vary from just a couple of users, if you will, to millions of clients and one central server, or perhaps many central servers. And whatever entity controls that central server also controls the information. Some very quickly, pros and cons of this model are, well, the centralized architecture allows for more control, access to more control. Searches are a lot more comprehensive. However, the system has single points of entry, and as a result, the network could completely collapse if one of several of the servers were to be incapacitated. The server-client model may provide out-of-date information or broken links. As it's the case, the server's database is only refreshed periodically. In a decentralized model, you have something where every user acts as a client, a server, or both, and that being labeled a servant. The user will connect to a framework and become a member of the community, allowing other people to connect through him or her. Users speak directly to other users with no intermediate or central authority, and no one entity controls the information that passes through that community. A clear example of this is Gnutella. And I'll go through these really fast. As an example, in Gnutella, you have, let's just say, a user named A who will make a request to other computers that are connected, that are close, and let's just call the computers B, C, and D. This user A will first make an announcement that, hey, I'm here, I'm looking for stuff. So we'll send a first layer request to these computers. These computers, in turn, will also send the request onto the next layer of connected computers. Of course, once A has announced that it's alive and the computers around them, B, C, and D, and the computers under them, sort of start shaping like a vine, if you will. These, then the computer A will announce that not only it's alive and that request comes back, but then there will be a searching of the contents of the shared directories of the peer network members. And if any one of the computers on the peer network, say for example, user D has the file that matches the request, then it will transmit the file information along with other information back to all the computers in the pathway towards A, where then a list of files matching the search request will then appear on that computer. Then A will then be able to establish a direct connection with computer D and directly download the file from that computer. The Gnutella model, which is the decentralized model, enables file sharing without using servers that do not actually serve the content themselves. This is another view into the Gnutella network, which kind of starts sort of illustrating how complicated this network can get. This is, of course, a very old graphic that I have here, but I found in my research a fantastic little tool called Gnutella Vision that if you ever get the time to download all the things that are necessary to visualize, it's very interesting. This gives you a real-time visualization of a peer-to-peer network. What I'd like to point out, which is interesting on Gnutella, among many other things, is this is a historical host count. The green, which is really the scrambling you see higher. It's interesting to notice this is from the year 2001, how I put a little arrow there on the left side, my left side, there, which kind of points the incline, the increase in unique hosts becoming part of the Gnutella network, really from about the time where Napster starts experiencing serious legal problems. If you notice at the peak right there from last year, around the summer, close to July, you have something close to more than 50,000 hosts. What's really interesting is if we go to this year, 50,000 hosts has become 500,000 hosts. And right about March of this year, you see this amazing increase in the number of hosts, and it's kind of come down a little bit after that, but it's just very interesting to see the exponential growth of this network. Gnutella per se is a network. Gnutella started from a protocol that then became widely shared. And Gnutella in itself is not really an application. It's a network. That's the best way of thinking of it. And when you hear things like BearShare, LimeWire, the newest, the preview edition of Morpheus, they're really part of this Gnutella-like network. Gnutella, per se, the name came from that purely decentralized network that was established about a couple of years ago. So for examples of this, for a purely decentralized, I'm referring to that iteration. Another example of purely decentralized network is Freenet, where it's somewhat similar to Gnutella, but when a file is transferred along the Vine-like framework, the file makes a copy of itself along the route. Along the route, each of the users will also be making a copy of the most copied file and would theoretically figure ways, have that be the easiest way of obtaining that file. The interesting thing about Freenet is that it's also implemented encryption to hide the originating point of the file. It's an open source project, and the vision of this project is to provide a system where all information, whether it's copyrighted or not, is to be distributed anonymously and untraceable in a peer-to-peer network. One of the pros of this project is that it really eliminates resilience in centralized servers that are potential points of failure. But also, I suppose there is some attractive in the anonymous nature of this and untraceable features of this. In a decentralized framework, there's, of course, a lot of pros and cons. Peers speak directly with no central authority. Nobody owns the network. Nobody can shut it down. System failures, like if one node fails, that can quickly and automatically be worked around. However, there's a lot of freeloading, which in a nutshell is really not necessarily all users contribute the same amount. There'll be a vast majority that do not contribute, and that has loads on the network in itself. Scalability is not very scalable, and of course searches are less effective. It can be very slow. To some extent, I was alluding to how the network started as purely centralized, and in the past year or a little bit more than that, it's evolved to where there's now this concept of controlled decentralization. And some of the newer applications that we see in this space include that. Now I'd like to go to the sort of hybrid, sort of controlled decentralization framework, where you have characteristics both of the previous frameworks I just mentioned, where a user computer can act as a client, a server, or a servant, per se. There are server operators, which can control which clients or which servants are allowed to access a particular server. And applications that we see in this space are Morpheus and Groove. Morpheus, really fast, is it gives you the full gamut, as opposed to Napster, who just gave you MP3s. Morpheus provides support for audio, video, image, document, and software files. It uses metadata, XML tags, to describe the contents of a file, thus making it easier to find things. It's largely decentralized, and it's, to some extent, it allows you to also find things really fast. Like Gnutella, but unlike Napster, Morpheus does not maintain a central context index and is not subjected to content filtering. Like Napster, but unlike Gnutella, Morpheus is formally a closed system that requires centralized user registration and log on. Two interesting things about Morpheus are two technologies that it uses. It uses smart stream technology, which is intended to address the issue of incomplete files, incomplete file downloads, which can affect systems like Napster and Gnutella. Files may fail to download intact for a variety of reasons. For example, one of them being loss of network connectivity at the matching serving the download, the machine, I mean. SmartStream implements a sort of like a failover system that attempts to locate another peer sharing the same file and automatically resume the download where it left off of the failed host. FastStream, on the other side, is another technology that is intended to solve one of the other primary issues facing decentralized peer-to-peer file sharing systems, slow downloads. When a Morpheus search engine finds that more than one active peer is serving a particular file, it associates the list of peers with the file for later reference. If the user instructs Morpheus to download the file, the system can distribute the download task over a list of peers, and thus relieving any one peer from serving the entire file, and therefore improving download performance. Fortunately, I don't have very much time to explain this, but Morpheus works to some extent, like I said, it's a sort of hybrid model. It really handles the concept of these supernodes that can act as local search hubs that build indexes of the media files that are being shared by each peer connected to the network. And the supernode manages the search requests on behalf of the peers, and Morpheus client computers can automatically elect to become supernodes if they have enough bandwidth and processing power. And users themselves can opt of running their PCs as supernodes. Once a Morpheus peer receives its list of supernodes from the central server, little communication with the server is required. Such a scheme greatly reduces search times in comparison to the broadcast query that's employed by the Gnutella network.
10 minutes.
Another example of a hybrid model, is Group, where it's really specifically designed for the workplace. I guess what I will mention here is the idea of a protected peer-to-peer environment it's appealing to the business sector, which allows businesses the opportunity to communicate in a more efficient manner in a secure peer-to-peer environment. And it can also be developed for the business empowerment. I guess what's interesting here is that there are applications, and Group is the best example of applications that are not peer-to-peer applications for the business environment. Moving from frameworks into functionality and applications, what's interesting to mention in a whole bunch of all these frameworks is how endpoints on the internet exchange information and form communities where there's a new set of collaboration and workflow opportunities. We see three things: edge resources that can be better utilized and are accessible in real time, and each of them have their own identity, so autonomy is definitely moved to the edge. It's somewhat complicated sometimes to categorize within the peer-to-peer space what different applications there are beyond file sharing. I'm taking this taxonomy here from O'Reilly and Associates, the publisher, who categorizes peer-to-peer applications within particular function areas, and these are some of them. And what I highlight here are also this new sort of category on development frameworks where the development of tools and actual infrastructures are sort of taking place. I have also put together, a condensed version of another way of how the Burton Group, for example, classifies peer-to-peer applications according to function and audience. A couple of words really fast on one of those functions per se. I like to clarify that peer-to-peer is not distributed computing. What gets labeled sometimes under peer-to-peer, and which is really distributed computing, is I suppose that where the fine line is that there are similar challenges and issues from sharing and taking advantage of resources that are available at endpoints, and how the power of these can be harnessed for computationally intensive problems, to mention one of the many things that can be done. Clearly in this area you see projects like SETI at home, Fight8 at home, Chen at home. I should mention that SETI at home often gets cited as a peer-to-peer application, but it's not peer-to-peer strictly speaking. It's really a rather inverted client-server system. But we also see the fine line with these attributes with grid computing and now e-science projects. there's lots of commercial applications as well as scientific applications in this space, and you see companies like United Devices, Entropia, Avaki, and a series of organizations in this space. Dr. Foster's talk a few days ago talked definitely a lot more in detail on grid computing. I'd like to pass really fast on some of the challenges with peer-to-peer, and could be also opportunities. Clearly one of the challenges is just architectural. What is the best structure to work with? Perhaps peer-to-peer is really finding the appropriate balance between centralization and decentralization, but what really scales? Another big issue is resource management. One of the things is if all users operated at the same level of technology, then a peer-to-peer framework could work very smoothly. Of course, that's not really the case, and results in not every user is going to be working at the same level of technology or network connectivity, and that results in bumps in the speed and efficiency of a peer-to-peer network. Another big issue is, of course, this as a hot commodity, as a hot resource, bandwidth. To some extent, it's particularly in higher ed, we see, some people might argue that when it comes to peer-to-peer, it would provide the best case for upgrading network capacity, but that's not necessarily a workable short-term solution. I think in this space, there's a lot of work that still needs to be done in these applications. Better network awareness needs to be built in some of the applications, perhaps thinking of involvement monitoring hooks that enable the management of nodes. But I think what's interesting here is that to some extent peer-to-peer is forcing for us to look for new solutions and new architectures in resource management. Resource discovery is another big thing. Finding things in peer-to-peer systems gets harder and harder where there's not a single standard format with widely replicated content like just MP3s. But if you're looking, say, for example, at expert knowledge in a wide variety of subjects, you cannot overemphasize the present importance of search architectures and metadata. I'll talk a little bit briefly on this peer-to-peer workshop, but there's a lot of work that's needed in the plumbing that would be necessary for peer-to-peer. The Internet 2 middleware initiative, to some extent, may provide some interesting things in this space. Security and trust is another big thing. How secure can one feel in a decentralized network? There are issues with privacy. Who can look at my computer if I'm using a peer-to-peer system? The spread of viruses, we've already seen that that's been a case. There are issues of trust where peer-to-peer applications disguise the source of data, thus creating a lack of accountability and reputation of source information. There's this fine line between how do I establish as a content provider a level of trust in the peer-to-peer framework, and how would my clients follow distribution rules, and how me as a client will also feel that I'm not being compromised by my content provider. There's a lot of work being done here. Different ways of addressing security and are involve encryption mechanisms, sandboxing schemes. Some of them also. Some applications are working on PKI-like ways. In corporate environments, there are some interesting things going on with applications like Groove and Endeavor's technology. I should mention that nevertheless, the prospect of peer-to-peer connections across organizations tend to give people nightmares about security and viruses. Standards and interoperability are another big. Generally speaking, there's a lack of standards coupled with the immense growth. This has really created some impacts in the management issues. An effort that sort of tried to set a set of standards was a corporate peer-to-peer working group that was started a few years ago. Unfortunately, the majority of the companies in that space, other than the big ones, went out of business a few years ago. And now I understand that this peer-to-peer group has moved under the Global Grid Forum umbrella. Interoperability between applications It's sort of being looked by implementing common protocols or perhaps XML-based standards. I should mention some interesting projects like Project Juxta, which is an open source initiative to let existing and future computing platforms of all types and sizes interact as peers. End-to-end and how to preserve that is another big issue on peer-to-peer. What is the architecture that will preserve this principle? There's an interesting relationship with IPv6 here that it goes beyond expanding addresses for peers, but to some extent it's interesting to think how IPv6 could offer support for those resource management issues that come with peer-to-peer. Okay, and of course there's ties with other technologies. I'm not going to spend very much time on talking on the other hurdles that give peer-to-peer a headache. Clearly the copyright issue is another one. And as we all heard Mr. Lessig on Monday, this whole notion of copyright, which has been brought up or clearly in the limelight by peer-to-peer, has a lot of implications here. However, I think the interesting thing here is this, there's a whole new paradigm of things that are happening, and I put an interesting cartoon there. You'll have to read it. I'll take just one more minute. The approach in the United States on peer-to-peer, my experience is, of course, with higher ed, is where higher ed has had what I would consider a lot more reactive approach to peer-to-peer at universities, and universities working as service providers to some extent for the students, for the staff, and for the people on campuses. Peer-to-peer has really moved universities to think of ways on how to meter and allocate resources. Lots of universities have opted for user education and cooperation, imposing limits on bandwidth, adding capacity, additional fees to cover bandwidth costs. There's lots of different things in this space, that's for sure. There are a lot of philosophical conundrums here and clearly good questions on how does the university ensure the delivery of what one consider high priority traffic and let all other traffic go, and how do we shape what we would consider non-desirable traffic, but how does one label that? Clearly we're seeing on both commodity connections and Internet 2 some interesting levels of what perhaps we will call this category of non-desirable traffic. There's an interesting study on that, which there's a URL there. In the United States, there's been, through several Internet 2 meetings, a variety of panels and birds of a feather to not just within Internet 2, but with other policy-based conferences. I was involved with an effort at the beginning of the year on exploring, perhaps in a more proactive way, the peer-to-peer space, perhaps with the goal of looking at how peer-to-peer could expand beyond this notion of file sharing and how universities could perhaps take a more proactive approach. Clearly, one of the goals from this workshop was to sort of look what was at this space. Nobody had done this before, and what was very interesting on this was to somewhat set a stage for not just people in academia, but in industry and possibly within the government to share experiences and suggest some future directions on how higher education could look at peer-to-peer and related technologies. I put some references here to the fantastic program that this workshop put together, as well as a summary there. Within the Internet 2 Quality of Service Working Group, in the past year, there's been very interesting work going on, particularly with the issue of bandwidth management and QoS appliances per se. And the last thing I want to say is just recently charter under the end-to-end performance initiative in Internet 2, there's been, and as also as a result of this workshop, and based on this sort of grassroots effort, there's been an Internet 2 peer-to-peer working group where very soon, I'm told, series of activities and areas of work will be announced. I will definitely encourage all of you, if you're interested in hearing what this group is about, to contact the working group chairs.
Okay.
I think I'm going to have to finish now. I think what's some final observations, I think, is just how clearly there's something here in peer-to-peer that expands beyond definition and applications. It's interesting to see where content is coming back to users, in the sense that users allow, if peer-to-peer to some extent is allowing users to participate in the internet again, sort of going back to that original version where everyone creates as well as consumes. Control is at the endpoint, at the edges, but what I really want to highlight is that there's a mindset change on how computing can be accomplished, and perhaps what's very interesting about peer-to-peer is that there are bigger ideological changes that are taking place. I think this opens a myriad of possibilities. There are challenges, of course, but I think challenges are also opportunities. And clearly for the advanced networking community, these could be very good opportunities. If you're interested in more, I put some more resources where one can go. I suppose I had worked on trying to have a limerick all worked up, which I'm sure I violated all the limerick rules, but since I'm running out of time, I'm not going to embarrass myself with that now. So okay. I apologize for taking a little bit more of time.
Thank you very much, Anna. Well, I think you gave a very good speech, an overview of all the peer-to-peer technology and all the issues related with it. I think we have a short time for some question. Daniel Karenberg first. Please give your name and affiliation.
Okay, I'm Daniel Karenberg from the RIPE NCC. Thank you very much. This was a very, very nice overview. I hadn't been sort of paying attention to this space, and it was quite instructive. What struck me, sort of coming from a distance, is that what happens here is actually that sort of not only the computing model is changing, but also the resource usage and resource, the economics are changing. And I was wondering whether since in the peer-to-peer thing you not only consume resources like bandwidth and computing resources, but you also provide them. And I was wondering whether there was any work going on in looking at models for actually being rewarded for that and paying for that in a sort of micro way, in a distributed way. Is anybody working on this?
Oh, yes. Thank you very much for your question. Yes, I think yes, there are a series of companies working in that space. I guess one of them that comes to mind has a really funky name. It's called Mojo Nation. That comes to mind as a system where it's a sort of hybrid type model where there's the sharing of information and collaboration, but really, as you point out, where the management of resources to some extent is tied into how much people contribute to the pool of resources, but also to some extent the system rewards those that contribute more resources, and the resources could be just say more CPU power. The way the system works, and I really haven't looked very much into it. I have to be honest with you, I haven't used it, but I understand that it works on this system of micropayments where the more I contribute, the more they call this, what you get back is called mojo. The more mojo you get for the resources that I contribute to the system. And of course, if I'm using a lot of these resources and I'm contributing a lot of these resources, I also get, it also ties in a system of reputation. The more I contribute, the better reputation I get to some extent. So Mojo Nation is one. I'll be happy to send more on more systems, but that's one that comes to mind.
One last question. No? Let me, Anna, thank you again very much. And And I encourage everyone here to discuss with Anna by email and to go to see all the references she identified. We are going to switch to the next speaker. It's Mr. Andrew Herbert. He is from Microsoft Research. He leads research in operating system, distributed computing, resource-aware networking. Is it right? Yes. Before going to Microsoft, you were with Citrix on advanced technology. Still right? Okay. And you are an active role in many standards and consortia for distributing computing? That's enough? You were. Okay. Andrew, please.
Thank you. Let's get the technology set up and we're in business. So I want to, I need to be wired up first of all, I think. Okay, we in business? No. No, can you hear me? No. Yep, that sounds good. Okay, yeah, we're there. So I want to pick up on some of the things that Anya was talking about, looking at peer-to-peer as an infrastructure for building distributed applications. And I'm going to report on some of the work that we're doing in Microsoft Research in Cambridge, work of my colleagues, Ant Rostrun, Miguel Castro, and Anne-Marie Kermarak. Also, work that we're doing jointly with Peter Druschel and his group at Rice University. I guess the place I'd like to start the presentation from, and I was talking to Roman Tirler when he invited me to come here, was we were talking about peer-to-peer and the grid, and he asked what Microsoft is doing in the grid space and how peer-to-peer might fit in that world. I think that the Microsoft view of e-science and grid computation is very much that we share the vision of trying to build virtual organizations, and that those virtual organizations are things you may want to put together very dynamically. A group of people sitting in a room with a batch of wireless cards want to become a community. A group of people in different companies working together on a project want to become a community. So we share that part of the vision, but I guess given the markets that we address, our focus is much more on business needs and science needs, but we see the technologies overlapping quite closely and clearly things that need to interoperate since much business uses science. So a number of things that we've done in the grid world. We've been working quite closely with a number of grid projects looking at how to use clusters of Windows systems for doing large-scale computations. Many of you may know, for example, Jim Gray's work on TerraServer, which is a large database system which carries image data of a large chunk of the surface of the Earth, allows you to query the database and extract images and have them joined together. That's quite an exciting project. Shows some of the issues in handling large amounts of data and moving around the network. We've been working closely with the Globus team, sponsoring their endeavors to make sure there's a Globus port on the Windows platform. And perhaps more importantly, and the most current activity, is working with the Globus group on the definition of the Open Grid Services Architecture, which is defining how to wrap up grid services as web services defined using the web services standards that industry is developing. Things such as SOAP for making your requests, WSDL for describe your interfaces, that batch of standards, looking at how we can use those described grid services and then interoperate in the web services world and the grid services world. And indeed, one of the things I want to pick up as I go through this talk is how we can link those ideas of web services into some of the ideas of peer-to-peer computing. And obviously, we'd like to see the e-science community leverage web services as they become available as part of their infrastructure for building their e-science. So that's the link to the grid, if you like. In terms of what we're looking at in Microsoft Research, the web services vision is kind of the current round of client-server middleware, focused very much on interoperability between different operating systems, different languages, different application development environments. And the focus is wide area integration. Much of the earlier work in middleware, Corba, DCOM, and so forth, the focus was much more on kind of back office, local area network integration within the enterprise. The web services vision is much more widespread than that. That immediately opens the questions of how we can extend that integration model to do more efficient sharing of information, more efficient collaboration across those systems and structures. So very much in the style of the last talk, we see a peer-to-peer service as a very attractive model for doing that, in contrast to today's server-based structures. If peer-to-peer is going to be successful as a way of achieving information sharing and collaborative applications, then there are a number of important properties that require. It has to be scalable and self-organizing. Scalable so that many people can participate, so that you can add additional people into the network, additional components, additional services. It has to be self-organizing. A peer-to-peer system that requires people to administer it is just going to be a nightmare. And indeed, we suspect many of these peer-to-peer structures will be there to support a whole variety of ad hoc computing needs, ad hoc information sharing needs. And the attraction will be people just join the system and the right kind of thing happens. Load gets balanced, resources get shared. It necessarily has to have a simple framework for the developer. If peer-to-peer computing is presented as some very complex set of APIs, very complex set of protocols, then people aren't going to develop the simple applications that grow the environment. And so the question really is, how simple can we keep the API? What are the core functionalities? What are the things we should do as part of the peer-to-peer infrastructure that make it easy to build the peer-to-peer applications? And clearly it has to fit in that framework of the web services standards, WSDL, and so forth. And so those are issues we're trying to address in our own work at Microsoft. I can skip this slide very quickly because the previous speaker took you through all the detail. Peer-to-peer is almost the wrong phrase to use because for certainly the computer user in the street, or maybe it's a computer user on the Clapham Omnibus, peer-to-peer is all about file sharing and music download. And you get lost in an interesting, but in some sense irrelevant discussion about content protection, lawyers, fighting Hollywood, and whatever else. That's not really an area that interests the particular strand of research I'm involved in. What the research community has been trying to do in that space is understand what's the general purpose framework. We have a number of protocols that people propose. We have a number of specific applications, like Morpheus, Kazan, Gnutella, and so forth. What's really underneath those? What are some of the fundamental ideas? And how can we start thinking of those as a set of components, perhaps middleware components, if you like, that we can use to build more general applications? And what are the new applications that those components might support? So it's a classic case of technology push and pull. Technology is being invented, people trying to work out what they can do with it, the usual question in search of an answer, and there's some applications out there which certainly could use a more general technology to support them. So to give you an idea of some of the kind of applications you can build with peer-to-peer system, in our own work, we have a peer-to-peer framework. It's called Pastry. It's called Pastry because it's the routing system for an application called PAST, which was the persistent archive storage system. One of these things, if you don't choose a name for a project wisely, it comes back to haunt you because everyone else says, what does Pastry stand for? And you can't say it stands for nothing. Say, no, it must mean something. We have our own infrastructure called Pastry, and on top of it, we've built a batch of applications, and they give you some idea of the kind of things that peer-to-peer is good for. The main one that we've been looking at in recent months is publish and scribe style event notification. The idea of there are a set of topics of interest in the context of network management. There might be various kinds of alarms that people want to know about status of things inside the network. There's a set of publishers who are people who are in the position to signal information about those topics. There's a set of subscribers who are the people who want to know about those things. One can think of other applications, obviously news groups, instant messaging, broadcasting share prices, a whole range of things in environmental sensing, where there may be many sources of information that have to be brought together and distributed. In a publish-subscribe model, the publishers don't have to know who the subscribers are. They magically throw their information into the pot and it somehow gets out to the people who are interested. So it's a very dynamic binding model. That's a very hard thing to do. It involves aspects of multicast. It involves aspects of load balancing. If there's an event everyone wants to know about, you can put a huge stress on the network as you try and broadcast that. There can be great asymmetries. There may be some topics that have many, many publishers, but only one subscriber, all the sensors that relate to me and that I want to know about. There may be other topics that are completely the other way around. There's one publisher, someone's stock price, but many, many subscribers, all the people who carry that stock in their portfolio. So trying to build an infrastructure that shares that work, balances the load of remembering the events, balances the load of communicating them, is a classic peer-to-peer task. The whole file sharing, document sharing area is one which has been obviously heavily explored. The systems that were talked about previously for sharing TV, MP3s, and so forth. It's a nice way of organizing a file system. A separate piece of work in Microsoft is a project called Farsight, which is taking the Windows file system and operating that in a peer-to-peer fashion. And the idea there is very straightforward. If there's a whole group on the network, if you look at most corporate networks, you discover about 40% of most people's disk is empty. If you count all the files that everyone has a copy of, that rather nice operating system we sell them, then there's even more disk that is essentially replicated content that you could get from someone else if you lose it. Then a nice way to solve the backup problem is copy your files onto a random set of machines, hopefully sufficiently random that they're not on the same power line as you. So if your building loses, if a building loses power, you don't lose all the copies. You've then got backups. You can go to any computer and find your files. Lots of interesting security questions to make work in that world. Lots of interesting questions about consistency and so forth. But essentially, you start seeing the file system as something that sits there in the network, and you just go to a PC and use the file system. Lost files are easy to recover, and it turns out that there's a huge amount of spare disk capacity that you get a good benefit from. And as soon as you start sharing files and thinking about that, you discover there's a lot more files that could be shared that people currently aren't because there was no benefit in doing so. So you kind of get an acceleration. In our own work, based on pastry, we looked at building a distributed archive for storing documents that had the property that the documents were scattered across the peer-to-peer network and sharing them in an even-handed way. Another nice application of peer-to-peer is web caching, a system we built called Squirrel. The idea here is very straightforward. Rather than using a proxy server to do your web caching, why not just look in other people's browser caches for the pages that you want? And so the peer-to-peer idea is divide up all the URLs that people in an organization have looked at, spread those across the web caches. When you want to access a URL, you go to the peer that's responsible for that part of the namespace, look in their cache. If they've got the page, you take it from there across your local network. If not, they have to retrieve the page from across the internet, gets in their local cache, and then available for other people to share. Turns out that performs as effectively as a centralized proxy in terms of performance. It has the nice property that as more people come onto the network, the cache grows with the size of the community, and so the load gets shared. It can also shrink down. So you haven't got the classic problem anyone running a network has of, 2 more users join the network and suddenly you're buying another proxy server, and then you've got to manage the multiple proxies and decide how to split the load and so forth. It's a very nice resource management exercise, and one that grows quite well. It also has nice properties if you're a mobile user. If you have a peer-to-peer system that not only will find you a cached page, but will find one in a cache that's nearest to you on the network, then if you move from, say, the Cambridge Research Lab to the Redmond Research Lab, you don't have the nonsense of updating all the proxy information in your internet configuration because you're now coming through a different homing point. It just will find the nearest cache for you and use it automatically. And no network administrator has to set all that up and organize it. Another classic example where peer-to-peer works very well is directory services, dynamic DNS type capabilities. We built a system called Overlook, which works in a peer-to-peer fashion and has essentially the model that as people are using the directory system, a little bit like Gnutella moving file copies across the branches of its tree to make the files nearer to the people who access them, we move DNS entries across the tree. So if there's a part of the DNS namespace that's being heavily used in one part of the network, it will get replicated out to that location to increase its efficiency. So those are some examples of peer-to-peer networks, also peer-to-peer applications. Out of those, we arrived at a view of what were the fundamental functions that we needed out of a peer-to-peer framework. The first one is content-based addressing. If you're working in a peer-to-peer system, there's a cloud out there that contains your stuff. At the highest level, you want to see that cloud as an integrated store, integrated set of resources. And so you would like to be able to address some piece of content in that network without having to know its precise location, because it may be moving around as the network changes. Most of the peer-to-peer frameworks do that by implementing what is essentially a distributed hash table. So if you want to find something, you assume it has some name, a title, a keyword, a unique identifier, a URL. You use that information, you hash it to get a key, and then you use that key to somehow search the peer-to-peer network and get to the computer that is currently hosting that key. So in the web caching example I talked about, the keys were the URLs. Who's the person who currently, if you take the URL, run it through an algorithm like SHA-1, that gives you a hash value. Who is the machine who is currently supporting that key is the person who operates that part of the cache. On top of that content-based addressing, a good peer-to-peer framework should provide you with the ability to manage caching and proxying dynamically. If in a peer-to-peer framework, there are likely to be many machines which are looking after the same piece of content. Typically, one uses replication to get resilience, replication to get availability, replication to allow you to connect to more local services. If you're going to do that, then the peer-to-peer framework needs to let you see how it's searching, how it's routing messages to the peers, and allow you to interpose caching and proxying so that local machines can stand in for remote ones to give hotspots much higher performance. That obviously then will give you faster access and also reduces the load on the site, which is in some sense the principal for any particular piece of content. Particularly, for example, with the publish-subscribe model. If there's a piece of news that has to be flashed out to the whole network, if you put that whole burden on the single machine, which is the primary site for looking after that topic, that guy's got to talk to everyone at once. And that's a huge load on the network accessible from him. If you can very quickly spread that out, then that reduces the link stress across the network. I've already hinted at replication and failover being important parts of those frameworks, and also implicitly the ability to do group communications and multicasts inside the framework. So the way most people are building their peer-to-peer frameworks is as an overlay network on top of the internet. We need somewhat richer routing semantics than the pure IP world can give us. We want to route to content rather than a computer. And we want to be able to do group communication and multicast. And unfortunately, while IP multicast is there and defined, it isn't widely deployed. I suspect because people don't know how to build, charge, and manage it are the issues. I can't see what the technical problem is. The attraction about an overlay network is it's a routing structure that lets the application participate in the routing system. It makes the network programmable in some sense. And indeed, many people have looked at programmable networks in other contexts. Obviously, the ideal overlay is one that's efficient. Using the overlay shouldn't cost you more than using the underlying network, self-organizing, scalable, and fault-tolerant. So can we try and use some of the peer-to-peer application ideas to build our own peer-to-peer infrastructures? So let me talk a little bit about pastry, and I've hopefully got a demonstration I can show you. The basic idea in pastry is the nodes participating in the pastry infrastructure are given a globally unique identifier, typically 128 bits long. How you arrive at that identifier depends to some extent on the semantics you want to attach to those IDs and the application. You may just invent a random number. You may take something like your DNS name and hash it to arrive at a random number. Depends whether you want the random number to be in some sense predictable or not. But the key point is every node in the system has a unique ID. Those IDs are issued at random. So if we were a set of peers in this room, we'd each have IDs, but it'd be extremely unlikely that any two of us would have a consecutive number because they're drawn out that big namespace. The API is really rather simple. There's essentially one function. You ask the infrastructure to route a message, whatever you want to send, to whichever node is currently alive that has the ID closest to a key. And so if I'm thinking of the web caching example, remember the key was the hash of the URL. The message will get sent either to the node whose ID matches the key, if there is such a node, and that node is up and running, or someone who's next to it. So the way we build in resilience is we typically arrange that the service is replicated over the set of nodes who have adjacent IDs in the namespace. Now, if we've got adjacent IDs in the namespace, but those IDs have been handed out randomly, those people are probably uniformly scattered across the surface of the Earth. So the replicas are at some distance to each other, but we know how to get from one to the other if we know the shape of the namespace. So we deliver the message to the currently live node with the closest ID. I'm going to go a little bit into some of the details of the algorithms. The key things I want to bring out are to make it scalable and efficient. There's clearly a routing table required to get that message from one end to the other. That routing table is about the size of the logarithm of the number of nodes in the network, so it's quite small. And we managed to route across the network using the knowledge in those tables in, again, the number of steps equal to the logarithm of the number of nodes in the network. It's a fault-tolerant architecture in the sense that the routing tables are automatically fixed when nodes are added, when they delete, or when they fail. So I'll show you through some pastry routing. Here's the basic idea. Suppose the node whose ID is 0112 wants to send a message with the key 2000. So it's trying to find the nearest node to 2000 that's up and running. The first thing we do is we essentially route by fixing the digits in the key coming down from the first digit to the last. So the first thing we do is find someone who's in the namespace 2xxx and ask them to do the next step of the routing. So what you can see across the bottom, the red lines are the nodes that exist. So you can see there are gaps in the namespace, and the numbers across the top show you the namespace divided up digit by digit. So there's, at the top level, I'm using 4 digits, 0, 1, 2, and 3. So there are 4 main divisions. Then those subdivide down by 4. So I'd have 0, 1, 0, 2, 0, 1, 0, 2, 0, 3 on the left-hand side. So first of all, I talk to someone who's in the 2 namespace to get the first digit resolved. I ask that second hop to fix the second digit. I'm now in the 2 part of the namespace. I'm now hunting for someone who knows about the 20 part of the namespace. So I get to 2032. I ask 2032 to find me the next node down in the 200 space. And it happens that he knows about 2001, which is the closest live node to 2000. Perhaps node 2000 isn't operating or hasn't been allocated. But I've got to node 2001, and so that's the guy delivering the service for me. So the information I needed to do that is captured in our routing table, and it's essentially a tree structure. For any node, I need to know at each level of the namespace, thinking of the names as levels, I need to know someone who is in the other domains that can exist at that level. So the example here, I'm using the node 102333102 as my example node. So at the highest level, I'm in the 1 namespace. I need to know someone who's in the 0 namespace, someone who's in the 2 namespace, someone who's in the 3 namespace. And indeed, we organize the routing table so that I know not only someone who's in that space, but the nearest person in that space to me. And that's kind of the invariant the routing table tries to maintain. So as I gather knowledge about the peer-to-peer system, if I discover there's someone else in the 2 namespace at the highest level who's much closer to me in terms of round-trip time, then I use them as my next hop for routing, rather than someone who's more distant. So I have an idea of locality in geographical terms, as well as the separation in namespace terms that comes with the names. And so each level down through the hierarchy, I need to know about my peers. So that's why the table is log to the base, log n of the entries. The other thing I maintain is the namespace set, the list at the bottom of the table there. Those are the names of my immediate neighbors to the left and the right. and I keep a track of some number of those. It's a parameter. The more of those I know about, then the more failures I can tolerate in the system and recover. And that's essentially knowledge of which parts of the namespace are allocated. Those are the obvious people to use as replicates if I'm replicating information across a set of key holders. And that namespace set actually is the critical part of the system. If I lose the routing tables, provided I've got the namespace set, I can go out and rebuild everything from the ground up. If I've got the routing table, then things are much more efficient because I haven't got to go searching around all the leaf sets all the time. So let me try and show you a couple of demonstrations, if I can wake this machine back up, of how some of these things work. Brilliant. And get rid of that. This is the pastry algorithm running under a simulator. The idea is all the red dots on the screen are pastry nodes participating in a pastry network. And I've set the system up so that I'm using essentially binary names. So I've got 0 and 1 in each level of the namespace. And what it's showing you is for pointer. This node here, which is a node in the peer-to-peer system, then the blue circles are the members of the leaf set. They're the adjacent people in the namespace. So if this guy's node ID was 00001, this might be 00002, 3, 4, or whatever. So you can see the leaf set is completely scattered across the surface of the Earth. So I've got good scattering of the distribution of the people who are looking after the content. So I should be able to find a local member wherever I am as a client of the system. I've got good replication properties. You could take out a continent, and I still got plenty of replicas left. The green lines are showing you the knowledge of the routing structure. So here's the node. There its neighbors in the namespace, the ones with the blue circles. The green lines are the entries in the routing table, and the thicker lines denote the higher levels of the name table. And you'll see on the map, for people higher up the namespace, then my routing entries are people much closer to me. Because as I'm doing routing, as I'm making that step down through the namespace, I want the first few steps to be with close neighbors, so that while I'm kind of hunting for the person who really knows where to send me, I'm doing that in my immediate locality. I'm not paying a long time in terms of the routing search. If I change the parameters of the namespace, and wake it up, of course it's all got nicely to sleep. If I choose to use 4 digits in each level of my namespace, you'll see that the routing graph now becomes much more compact. Several levels of the tree get me there in early steps very quickly. I've got my neighbors scattered around. So that's the routing system. And if I show you some routing, if I send a message from here, let's go to New Zealand. You'll see the routing algorithm, using the information in the name table, makes a couple of short steps, and then gets to a node who has the information to get me to my final destination. And perhaps if we show a couple more things in the last few minutes of the talk, I can show you how we can use that knowledge to build some multicast structures. Obviously, for that technology to work, I've got to be able to add new nodes in the system and maintain all those data structures in the routing information and do so in a robust way. It turns out to be actually a very simple process. If I want to add a new node in the system, someone whose node ID is X, then provided I know someone who's playing in the pastry world, I go to them and ask them to send a message to X. X isn't there yet. What they're going to find is the people who will be the neighbors of X when X is eventually in the peer-to-peer network. And those are precisely the people whose routing tables you want to look at, because they will know about all your friends and neighbors through that tree structure. So to join the group, you work out what your ID is, random number or whatever. You then send the message to yourself and then talk to everyone who routed to the guy who turns out to be your neighbor. You go to your neighbor, you ask him to thread you into his namespace set. And essentially what goes on is around the people who are about to become your neighbors, all those namespace sets shuffle to create the hole for you to join in. they send you information about their routing tables, and then you're in business. You've got a routing table, you're correctly in the leaf set, you can join in the replication games. So it's a very simple algorithm. I'd like to show you an application built on top of that pastry structure to show how you can use it as a framework. This is the Scribe peer-to-peer publishing system I talked about. If you remember, I described it as a model in which subscribers can express interest in some topic. It might be a news group. When a publisher sends an event to that topic, that event gets notified to all the subscribers. I may have multiple publishers sending that event to multiple subscribers. And so there's decoupling between those two. The challenge is how to multicast the notifications efficiently. The way in which this is done in Pastry is the topic is just hashed to a key. So we randomly assign responsibilities for different topics across the nodes in the Pastry peer-to-peer network. And we use the routing tables essentially as the multicast tree to cascade the messages. And we pass the events down through the tree. I can probably show you that easiest in a couple of slides. If I'm creating a topic, I take the topic name, I hash that. That produces a key, perhaps T. I look in the Pastry namespace. I've shown it here as a circle. It's just a more convenient graphic representation. I find the node whose ID is closest to T, who I call the root, and that root node acts as the key holder, the principal for looking after the topic. When users subscribe to a topic, imagine here the topic is being looked after by node 1100. When someone subscribes, as the message routes through the Pastry network, the nodes doing the routing remember who the subscribers are and essentially compute the backward path as we go. And so I build the first path from 0111. If 0100 subscribes, the routing algorithm takes his connection to 1001, and at that point I don't have to go back to the root anymore. I've already found someone else who is, by definition, in the multicast tree for that topic. So I just ask them to forward the message to me rather than troubling the root for that information. So I'm dividing out the work of remembering who's interested in this topic. If 1011 joins, they perhaps route higher up in the tree and have their information. When it comes time to disseminate the event, when I'm publishing on the topic, we just use that tree as the way to send out the messages. So the event comes into the system. The first node sends it down to the next node. He cascades it out to the next set of nodes, and they cascade it down through the system. The effect you're getting there is you're transmitting the message in multiple rounds. In each round, you have a small number of messages. The number of messages is increasing round by round, but the rounds are getting spread out across the network. So it's having the right property. As you're building up the load in the network, you're also spreading it across the network, so the average utilization remains quite reasonable. We've recently done a content distribution system, which is kind of Scribe done backwards, which is how we can route content to one person by having lots of fragments coming from many places to get aggregate bandwidth that way. I can very quickly show you Scribe on here. It's the same infrastructure. If I want to add a topic, Tarina, then the topic gets assigned to the blue node there. If I have a batch of subscribers who are interested, let me assume that much of North America is interested in this topic. Then when I build the multicast tree, you'll see because of the locality properties of Pastry, the tree is quite dense. So these are the leaf nodes at which I'm going to be doing the final steps of the dissemination. And the number of links I've actually built across the long-haul links are quite small if I was to also have an Australian community of interest. You see I get very similar properties, and if there are people in this part of the world, Asia, who are interested, it has all the right properties I need for building a scalable architecture for information dissemination. So, to wrap up, what I hope I've shown you is that peer-to-peer techniques are a good vehicle for building wide area information sharing and collaborative applications. That you should think of doing these in terms of an overlay network, a network in which the applications can participate in the routing, the replication, the recovery, and so forth. The particular system I've talked about, Pastry, developed by people at Microsoft and Rice University, is a very efficient framework for doing that. It scales, it's self-organizing, you can add and remove nodes, it looks after itself without being administered. It's certainly a peer-to-peer system. There are no super nodes, no special nodes looking after it. It has a very simple interface for applications. Ask it to route a message to a key. Think of the infrastructure as a hash table. The other part of the API is an upcall. If you're a peer-to-peer node and someone routes a message through you, you can elect to be told that message is going through, and that's the thing on top of which you can build the caching and proxying capabilities I talked about. So it makes it very easy to build powerful peer-to-peer applications. If you want to know more about Pastry and some of those applications, if you look at this URL, then you'll find copies of papers describing those things. You can access the simulator that I've been using for the demonstrations. Thank you.
Thank you, Andrew. I think we can take one question, but before the question, I have to announce that Daniel Karenberg can make a talk about new DNS features. I don't remember what it is exactly, but it will be a 10 minutes or 15 minutes of more speech, which could be very interesting, okay? So sorry if the coffee will be a little bit later, but Daniel will be giving his speech right away. So, question, please. One question.
In the Pastry routing, why did you choose a decimal hierarchy and not, for example, a power of 2?
It doesn't matter. In most of the practical implementations, we usually work in base 4. In base 16, 2 to the 4. That happens to be convenient. In terms of talking about some of the things on the presentation, using binary gives you quite deep trees, which convey some of the points slightly better. It doesn't actually matter. I sometimes do an audience demonstration with a ball of string and hand out numbers, and then I typically use base 3 because you've got about 100 people in a room. That again gives me a nice distribution of the numbers. But it's essentially a trade-off between how big you're prepared to have the routing tables get and how many routing hops you're prepared to tolerate. So the larger you make that factor, it's the number B across the top there. The larger you make that number, the bigger your routing tables are, but the fewer hops it takes to get across the network. And at 16, routing tables don't get very large. They're a few kilobytes in size. Okay.
Well, unfortunately, I think we will have to stop here. Thank you, Andrew, very much. And I invite you to talk to Andrew after this session. Thank you. Well, Daniel, I will let you introduce yourself. Anyway, I think everyone here knows you.
Okay. Hello, my name is Daniel Karenberg, and I was sort of asked to say something about work that interests me because there was a fear at the beginning of the week that this session would have no speakers, or at least only one or something like that. So what I'm going to talk about is some work we've been doing together with RIPE-NCC has been doing together with the Nelnet Labs. And it's not about new features in DNS, it's just about the new DNS implementation. And I realize that I don't fit really into the theme of this session, but what I'd like you to do, if you, unless you want to go for coffee, is to basically take note of this and maybe tell it to the people who are responsible for running the DNS services in your organization. And I promise that I will not take more than 10 minutes. I'll probably be much quicker. Basically what we've been doing is we've been writing another DNS server. Well, why the hell would you do this? I'm going to tell you. I'm going to tell you very briefly what it is, and then I'm going to tell you who should use it, and more importantly, who shouldn't. Why? Well, actually what was realized a long time ago, but what was in the discussions sort of about stability and security of the Internet, and at the end, that got intensified somehow at the end of last year, is sort of that we're all depending on this not distributed, not peer-to-peer system that's called DNS. It's a hierarchical database. And actually, the root name servers, which are at the top of that hierarchy, happen to run essentially the same application code base for their DNS service, and that's bind 8 at the moment. And there was a need there is a need for basically diversifying this a bit in order to make it more resilient. And that's the basic reason why we did NSD. There are not really very many DNS implementations that are sort of industrial strength, and there's definitely only one that's open source. And we very strongly believe that what runs on this particular piece of infrastructure should be open source. And then there's a number of minor reasons, and I tried to express that with the font size. Actually, what bind does, it's sort of what in German we call the eierlegende Wollmilchsau. It's the thing that does everything. And what actually needed for a root name server or a name server sort of publishing a top-level domain is much less than what's implemented in bind, because bind is also a caching machine. It can be used as a caching forwarder. It can do dynamic updates and all that kind of stuff that you really don't need. So we wanted to do something that's more simple. What comes with more simplicity usually is better performance, so that's nice. And yes, as I already said, open source. So what is NSD? NSD is an authoritative-only DNS name server. So it's not something that you put in your organization and point all your resolvers to, because that's what usually is a caching forwarder. It doesn't do recursion. So if you ask it a question and it is not authoritative for the answer, so it doesn't authoritatively know the answer, it will not answer it. It will refer you to another name server that has that. It doesn't do caching, so it will not, sort of some information it has learned somewhere, cache it and then serve it. It doesn't do dynamic updates, and at the time I was making this presentation, it didn't do zone transfers, but actually the current alpha version does zone transfers. It was implemented from scratch. That was one of the things that we wanted to get the diversity going correctly. So we actually very consciously didn't look at anything else, and we didn't use anything else. And the design was sort of, a bit more for high performance. The other thing is that at the moment, there's still not fully specified, but getting there anytime now, DNS security standards. So how do you do, basically, how do you make sure that the information you get from the DNS is really the information that the authoritative party has published? And this design is actually ready for DNS. And it's well tested, and that's my little pastime. So if anybody's interested in talking about sort of how you test DNS applications, I've been doing that for the last couple of months, and that's been fun. I've got a whole other talk about this, but I'm not going to bore you with that. The basic design is basically what you have if you publish DNS information is you have a couple of zone files. That's where it says, in this particular zone, say .ie. The University of Limerick is called University of Limerick and gives information about that, where are their name servers, where their mail servers and things like that. These zone files you want to publish, and the way we did NSD is we did it in two steps. First of all, we have a zone compiler, which basically computes all the responses that a name server could generate based on information in those zone files. So it makes a transformation from the format the publisher uses into the format that actually goes over the wire. That's not so trivial because of the specific encoding used in DNS and name compression used in DNS. But anyway, so all the answers are that these servers give are precompiled, if you wish. Then we take the database of those responses and have a daemon process, and the sizes here are chosen to express something. Take a relatively simple daemon process that will then serve these things to the internet, to the clients. So much of the work of sort of verifying consistency of the zone files, doing some complex operations on the zone files to generate the answers and so on are done in the zone compiler. And the basic work that the daemon has to do is just get the query, look up the response in the database, and then copy the response to the wire. That makes it go very, very fast, especially now since in the context of DNSSEC. We basically measured the performance, and that's the work I did. Went along and built a test lab where you can actually play various loads at a server and see sort of how it reacts. Not only look at the performance, like what I'm showing here, but also look at what the differences in responses would be between different implementations and things like that. And what we find is, what you see in this graph is, on the x-axis, you see average queries per second. What I did here is I took real-time trace data of queries that were sent to k.rootservers.net, one of the root servers, and I played it back at various implementations at varying speeds. And the speed is on the x-axis. So where it says 10,000, the average number of queries per second was 10,000 queries per second. And on the y-axis, you see the number of answers that were generated. So to the left of the graph, you see that 100% answers was generated for the low loads. On the right of the graph, you see basically how many answers the implementations could generate when the load was increased. And there you see the yellow line gives you the current bind 8 implementation, which is what most people use who use bind. And you see that it sort of, first of all, it copes very well, and then it has a very steep decline. To the left of it, the triangles are the bind 9 implementation, and that performs even worse. And there's been a lot of discussions, for instance, in RIPE about this, why this is, but I personally think there's two different explanations. One is sort of the more technical one. It has to do some more things to be DNSSEC ready. You cannot put DNSSEC into bind 8. They did some additional stuff to make it viable for DNSSEC. That made it slower. And the other reason probably is what's called the second systems effect. I mean, they knew a number of shortcomings of bind 8 and said, okay, we'll do the perfect system, and that has performance implications. Again, this is not to put down those implementations, because they do more than NSD does. They also do the caching and all that kind of stuff. So they can be used for applications that NSD can't be used for. And then the blue dots is NSD, and you'll see that it performs much, much better. And also the characteristics of the deterioration in performance are a bit more benign than the sort of very steep decline that you see in bind. Some people in the RIPE NCC said, no, if you tell this to normal people, they will not be able to interpret those graphs. Well, we're at a sort of scientific conference, so I don't think that applies here. But we also made the marketing version. And that actually, the last thing is sort of when we ask ourselves, and we started this whole project at late last year, basically triggered by the fact that everybody agreed more or less, yeah, another implementation is needed, but there wasn't really a commercial incentive for it. And then we said, okay, well, we have some people working on DNSSEC stuff, and they're delayed by the lateness of standards. So let's do this. And now we're mostly done in the alpha implementation. And we ask ourselves whether the goal has been achieved. Well, code diversity, I think we have achieved that. We have a totally new design. And the test results, which I haven't shown you, the semantic test results show that we have bug diversity. So basically, we have other bugs than bind has. The simplicity, I think, yeah, the design does that because the daemon is kept as small as possible, and we have no creeping featurism. We don't put features in there that are not needed for an authoritative-only name server. And the performance, well, I showed you. And it's going to be open source, or it is open source, a BSD license thing. Who should use it? Well, publishers of authoritative zone info, like root name servers, TLD servers, organizations that publish DNS data could use this, and then could use bind, for instance, or something else for their caching name servers. Who should not use it? Well, people needing recursive name service, basically so with, answering end-user queries, and those servers that really need dynamic updates. But I would postulate there are not so many of those. 1.0.0 beta is available, and 1.0.1 alpha is available, and those people doing DNS should definitely have a look at that stuff. Other information can be found here. The various releases of it can be found at analabs.nl, and if you don't, then you can find my coordinates and get it.
Thank you, Daniel.
Please tell the people who are doing DNS in your organization.
Yeah. Unfortunately, we don't have time to take a question. I thank you. I thank you again, our three speakers. Anna, can you hear me? Anna, can you hear me?